A warm welcome to my presentation, everyone. My name is Jorge de Heuvel and I conduct my research at the Human and Robots Lab at the University of Bonn in Germany. Robots should be personalized, and let me tell you why. Robots should be personalized because users might have a personal gold standard of the interaction. So imagine closely collaborating with your personal robot at home or at work, and then ideally the interaction should be as comfortable and natural as possible. And users may have individual preferences about the interaction with the robot, such as where the robot traverses a home or how they approach. And here, personalization will be a key factor. So today we talk about the preference alignment of robot navigation. In this work, we learn a preference reflecting navigation controller that relies mainly on depth vision. Using a virtual reality interface, the user intuitively demonstrates preferences to the robot by drawing trajectories right onto the floor using a handheld controller. To learn, a TD3 reinforcement learning architecture is used with an additional behavioral cloning loss on the actor network. Furthermore, a separate demonstration buffer is used that provides the agent with demonstration trajectories throughout the entire training process. The robot-centric state space captures information about the position and presence of the human in the robot's field of view. Also, the goal position is provided. And most importantly for 3D scene understanding, a low-dimensional representation of the robot's depth camera is included. At the bottom, you can see the variational autoencoder that compresses the depth image to a latent representation of dimensionality 32. An LSTM predicts the next latent and human pose in the robot fields of view. To demonstrate, the user draws preferred trajectories onto the floor in virtual reality. The user's dynamic motion here is also recorded. And later on, the data is used in the learning process. Let's look at the qualitative performance of the controller. The robot has to avoid the dynamic human, denoted in red, while navigating from the start, that is the black dot, to the goal, blue star, ideally along the demonstrated path, and that is the orange line. In the couch scene on the left, the robot should navigate at the opposite side of the room along the cupboard. And around the suit in the middle plot, the robot should take a right-hand turn around the armchair. And in the entrance scenario on the right, the robot should take a left-hand turn while the human is passing along. Let's get a better understanding by looking at an animated map. Right, the visualization of the robot's perception is shown. And here we can conclude that the robot successfully reflects the demonstrated preferences on its way to the goal. For the quantitative analysis, the controller was evaluated for different perception configurations. And I would like to draw your attention here to two key results. Firstly, the only VIE architecture generally outperforms the LSTM prediction architecture. And secondly, if you provide no demonstration data throughout the training, the performance actually deteriorates. So the demonstration data also helps the performance of the controller. Let's now look at the ablation performance of the controller. We were interested what would happen if we were to remove items from the scene, such as the furniture or the dynamic moving human. And here on the left-hand side, we have a scene where there previously was a human, and the human was approaching the robot from the robot's goal position to the robot's start position, basically along the armchair. And now that the human is not in the scene anymore, we still get preference reflection, but the robot also traverses closer to the armchair. And secondly, what would happen if we remove the furniture from the scene? So here we have the approaching human without the armchair, without any furniture in the room, and the robot would now travel on both sides around the human. And thirdly, what happens if we remove both the human and the furniture from the scene? The only thing that is left here is basically the shape of the room. And interestingly, we still see preference reflection. So the preference reflection seems to be anchored also partially in the room shape and the goal position that is provided to the robot. Now, if you want to measure how well the robot actually reflects the demonstrated preferences, you need a metric. In this paper, we developed such a metric, and it's called the deviation-aware Frischier distance. Here in the plot, you can see that it only really makes sense to compare the similarity between the robot navigation and the demonstration trajectory until a certain point, and that is when the robot starts to deviate from the demonstrated trajectory. I will not go into the details here about results, those are to be found in the paper. For further quantitative results, ablation studies, and details on our preference metric, you're kindly invited to have a look at the paper. To conclude, we demonstrate how to learn a preference-aligned navigation controller that relies on depth vision. Our virtual reality interface allows for the intuitive demonstration of navigation preferences under dynamic human motion. And by introducing the deviation-aware Frischier distance, we provide a metric to compute the quality of preference reflection. We like to personalize technologies that we use every day. And now we can also personalize mobile robots. For further discussion, feel free to get in touch with me. The QR code here provides all of my contact details. And I would also like to invite you to have a look at our website for more research.